Good morning. Well, I tried to write the number where everyone could see it, but I didn't. Let me try again. 1, 2, 2, 8, 6, 6, 2, 0. There's my cat getting in the middle of everything. Okay. 1, 2, 2, 8, 6, 6, 2, 0. I'll put it in the chat. Okay, well, thank y'all for coming to the Zoom. At least we know how to do this now after the pandemic. When we had to, so much better than getting out in the ice. And anyway, I have a work at your own pace learning catalytics. It's got 10 questions, I think. So just take 5 minutes and do the ones you can. It's fine with me if you work together, but you'd have to talk. I don't know. Maybe you can text everybody, but anyway. Are there any questions? Can you get in your learning catalytics? Everyone good? I've got 13 people joined. And let's see. There are 22 of y'all here. And 13 people have gotten in. So please go ahead and get into Learning Catalytics. You go to your Pearson, click on the Learning Catalytics. The code is in the chat and it's up here on the board. 122866620. Just take 5 minutes. Yeah. Let me see how y'all are doing. Okay. All right. It looks like you don't know what your meridian is. But you're doing well on everything else so far. All right, I've had one person ask if they have to buy Learning Catalytics. You should not have to buy Learning Catalytics if you have access with eText. If you can get into Pearson and do assignments, then you should have the access to Learning Catalytics. If you don't, send me a screenshot and let me know. Not just one screenshot of you going to Pearson's homepage and then going to Learning Catalytics and then show me what it says if you can't get in. Did anybody, were you asked for the password when you went on the Zoom link? Just tell me in the chat, anybody? Thank you. Okay. Finish up if you haven't. Okay. Let me see how you did. It's still going to be open. All right. I am going to go over the first one because y'all are not doing well on that. Okay. You can go back and see the answers after the session closes, but the very first one says, in your local sky in Memphis at 35 degrees north latitude, the sun crosses your blank around noon. And the answer is your meridian. Your meridian. It's not your zenith. 60% of y'all think it's your zenith. Here's why it's not your zenith. Unless you are between north 23.5 degrees and south 23.5 degrees latitude around the equator, the sun is never going to be at your zenith. Your zenith is straight up. And so the sun is always going to be south of that, even on summer solstice day at noon. But it will cross your meridian around noon. Your meridian goes from the north point of your horizon through your zenith to the south point of your horizon. So it's a ring, it's a semicircle, and you can see it in the picture on the next question. The next one has the picture, and the meridian is actually in pink. So let me share my screen. Okay. So here is your horizon. Here's the north point of your horizon, the south point of your horizon, and your zenith. And the sun is always going to be somewhere south of your zenith because you're above 23.5 degrees. I know that it's easier to picture things when you have a model or something, and I don't have my models here at home, but I do have some animations that I'm going to go over with you, but please ask me questions. And you just unmute and ask me questions and then mute again, okay? If you don't understand something, you can also try putting it in the chat and I will try to check it, okay? I'll try to check it. But sometimes when I'm lecturing, I'm not great at that. Okay. So that is open for the rest of the class. If you haven't finished, just finish before you're done with class. And I'm going to go to, I had in my notes that this is where we stopped in the slides. So I'm going to back up just a little bit. And if you're not talking to me, please mute yourself.
What if we all, do you want to watch the piano's house?
No. What was that? Mr. Trunser, were you talking to me? If not, just mute. I'm going to mute everybody. I muted everybody. Okay. So if you've got something to say to me, unmute. All right. Okay, I'm going to go to the modules. Oh, this is not your class. Hold on. I had your class, but there we go. I'm going to go to the modules and show you. Let's look in the module for chapter 2. I know that you can see these on your own, but since I don't have my models, we're going to look at some of it together. Okay, so in this one, the reason for the seasons, this is a video of me teaching, and about the I think it's the 17-minute mark. Let me see. Look at a longer time. You see the sunset colors right there. By years. During different times of the year, summer and winter. And okay, so there's this. I'm going to mute. So I'm going to make it 0 latitude. That means this person is at the equator, and it shows a person at the equator. Can you hear that? And for time of year, I'm going to pick.
Yes.
Thanks. Well, let's see. I'm going to pick the equinox. All right. So someone. Okay. So I'm going to pause it for a second and talk to you. It looks like I have there's a latitude bar over here, and I have picked 0. So I'm at the equator. And the time of year is determined by where the Earth is going around the sun. And right now it is at the equinox. And I will, at one of the equinox, it's the spring equinox. And this part shows you that the dark light line goes straight through the North and South Pole. This is a north view of the Earth with that dark light line going right through the pole. And in fact, everyone all around the Earth has 12 hours of day and 12 hours of night at the equinox. But in addition, someone on the equator has the sun coming straight down and it's at their zenith. If someone is on the equator, the sun is directly overhead. Now we're going to go on. I'm going to move things around, and in a minute we'll be at Memphis at 35 degrees north. So I'm going to go ahead and continue right now. Lives on the equator. At equinox, the sun is directly at their zenith. How is that going to be when we're talking about December 21st? What's happening on December 21st? We've got the winter solstice for the north and the summer solstice for the south. This person's on the equator and the sun is coming in at an angle. Okay, I'm going to pause it again. So I move the Earth over here and the axis is tilted so that the axis is totally in the dark. This is at winter solstice. And at that time, the North Pole is in 6 months of darkness. And you can see that in this picture, you can see that as the world would turn on its axis, that the part around the North Pole is going to stay in the dark. You can also look at this picture here and see that the North Pole is in the dark on summer solstice day. For anyone further north than 23.5 degrees, which includes us, I've been saying summer solstice, and I apologize. It is winter solstice. I am so sorry. The North Pole's in the dark during winter, not summer, and I've been saying it backwards. I apologize. Okay, so I've got it over here. Someone on the equator is going to see the sun coming in at a lower angle. It's not at their zenith anymore. But for anyone above 23.5 degrees, that's going to be the lowest that the sun ever is all year in the sky. So let me go ahead and play it. What if we go to the other solstice? Now we're at the summer solstice. It's coming in from the other angle. But when is it actually directly above? On the equator? At an equinox. So it's directly above equinox. What if I go to on the equinoxes? Spring equinox, I've got the same thing. Now let's move our observer to Memphis. Now we're going to Memphis. 35 degrees north. And you'll see that the sun is never at our zenith during the year. 34, close enough. Notice what happens during the year. When is the sun directly overhead in Memphis? Okay, well, that's the lowest that it ever is. And, well, it's almost, but not quite, is it? It looks like now it's going back down. It looks like it's never directly overhead in Memphis. The lowest point is December 21st. Let's look again, just to make sure. You see the sun is never directly overhead in Memphis. That is because the highest latitude that it can be directly overhead is 23.5 degrees north, and the lowest latitude it can be directly overhead is 23.5 degrees south. We're at 35 north.
So it's never going to be at our zenith. Never going to be at our zenith. However, if I were to go to a latitude of 23 degrees, that's a different situation. 23 degrees.
23
north.
degrees north.
Let's see.
It
is the
should
sun
get to
gonna
the
be
zenith
overhead at any
one
point?
time.
And yes, right there.
On
June,
summer
the summer
solstice.
solstice. And if I keep going, it's going to go back down. So right there at 23.5 degrees, it just gets overhead once. What if I'm somewhere in between 0 and 23? Whoops, that's not what I meant. Okay, here's 18 degrees north. How many times do you think the sun is going to go through the zenith in a year? Let's take a look. It's going to go through once on its way past 18 degrees north, but it's going to get all the way up to 23 degrees. So as I keep going, it's going to pass overhead again on its way back down. So anyone living between 23 south and 23 north, except at 23 south and 23 north, you're going to see the sun at their zenith twice a year.
Twice a year.
Okay, that is all the animations for section 2 that I wanted to show you.
Okay, so I'm going to close that. You might say, why didn't I just show you the animation directly? It was a Flash animation and Flash is no longer supported. So I just had to do it like that. Now there is an unnarrated animation of that same thing. And you can see it a little bit better, but it's a little blurry. So if you want to look at it without me talking about it and just notice things yourself, that is available in your module 2. All right. I'm going to go back to the module 2. There we go. All right. Just going to show you around. Here's the animation for the overview of the whole chapter. I'm not going to play it. You can look at that yourself. I highly recommend it. Then you've got your PowerPoints, and then you've got me teaching each of these sections from chapter 2 from a few years ago. Then this we haven't looked at. I don't think I played it for you Monday. Maybe I did. Maybe I did. This is what the sky looks like as the world turns in both hemispheres. So this is from the northern hemisphere. I think I did show this. You can use this part of the Big Dipper to find Polaris. And if we watch our sky during the night, it looks like everything is going around Polaris counterclockwise. If we go to the southern hemisphere, we don't have a pole star, but we have a spot in the sky that everything goes around. And the Southern Cross points at that spot. And it appears to be going clockwise. It's because we're in the southern hemisphere looking up that it looks completely different sky, and also different rotation because we're in the southern hemisphere. Okay, let me go back from that. I may have shown you that. All right, let me see what else. That's what we just looked at. Okay, we've got some other things about later in the chapter, so I'm going to talk about it first. And then we can go back and look. So let's go ahead back to the chapter. And I'm going to pick up here. And I do have an animation of this. I think I showed you this, but not the animation. So As the Earth goes around the sun, let me get to slideshow. Okay, as the Earth goes around the sun counterclockwise when viewed above north, the daytime side is always towards the sun and the night is away. So as the year progresses, our nighttime sky, we're looking out at a different, in a different direction. And the constellations in our plane of orbit, called the ecliptic plane. I didn't ask about that, but that is a really important plane for you to know because it's the one formed by Earth's orbit around the sun. All of these constellations that are right along the ecliptic are called the zodiac. And you can see Virgo and Libra and Scorpio and so on and so forth that are familiar. And I do have an animation of that, but I'm going to go through some more slides before we go find that. So in summary, we looked at the celestial sphere. We said it's divided into 88 regions. The sky, the whole sky, is divided into 88 regions called constellations. And we can specify the position of an object in our local sky where we've got our horizon and we've got our zenith, and we have a meridian that goes through our north and south points. So from our local sky, if we just look at anything in the sky, we can start at the north point of our horizon and swing around a certain angle, and that's the direction. The altitude is how far up you have to go to be looking at it. And remember, distance does not matter for being able to locate something. So altitude and direction. And why do the stars rise and set? Because the Earth is rotating. Our constellations not only depend on our latitude, but also on our time of year. And that's what we were just looking at. So then we're talking about the seasons. We've already talked some about the seasons. Do you think Earth is closer to the sun in summer and farther from the sun in winter? Just think about it for a minute. If you want to share it, put it in the chat. Is this true or false? Okay. Nobody, okay. Someone says true. One brave person. Another person says true. False. Okay. Okay. It is false. And I will tell you why. If you think about, let me go back to a picture. The whole Earth is a certain distance from the sun at any one time. That distance varies as the Earth goes around the sun. But at any one moment, the Earth is one distance from the sun. And that includes the northern hemisphere and the southern hemisphere, regardless of the tilt. And so we can't, so at the same, let's just pretend, let's go to the summer solstice for us in June. It's the winter solstice in the southern hemisphere, but we're all the same distance from the sun. So that's why that's not it. It's really tempting to say it is. It also just happens that we do get closer and further in our orbit because it's an elliptical orbit. It's not a perfect circle. It's almost a perfect circle. But we're actually a little bit, the Earth is actually a little bit closer when we have our winter than when we have our summer. Okay. All right. So the real reason is the axis tilt. We always have opposite seasons in the two hemispheres. And the reason is the axis tilt. All right. This is not an animation, it's just a slide, but it shows pretty well the positions of the Earth at, this is summer solstice for us, winter solstice for Southern Hemisphere, the equinox. That's, again, remember that at the equinox, the light dark line goes straight through both poles. The Earth turns once a day. So everybody at equinox has the same 12 hours and 12 hours. Now I'm going to ask you something. What if we were at the North Pole? What if we were at the North Pole? How many sunrises would we have a year? And when would they be? Just think about that. Just think about that. So the Earth here is at summer solstice for the Northern Hemisphere. It comes around here and it's at the equinox. So that's the fall equinox that's in September. Keep going around and we're at the winter solstice for Northern Hemisphere. And then we keep going around and we're to another equinox, but this one is the spring equinox. So ask yourself, if the pole is in light or dark, and when that changes. So it's clearly in the daytime during summer solstice. And as we get closer and closer, it's getting closer and closer to the light dark line. And at the fall equinox, what's happening to the pole? Is the pole going to move into light or dark then? Anybody? Let's come over here to winter solstice. Is the pole in the light or dark there? I hope y'all can see that. Thank you.
Let's
Okay.
say, I think it's the dark.
It's in the dark over here. So what's happening at the equinox? Is it having a sunrise or a sunset or something else? What's happening right there at the North Pole? Poles in the light over here, the poles in the dark over there.
The sun is setting.
The sun is setting. And that is the only sunset of the entire year at the North Pole, which has got to be, that's got to be so strange of an experience to have one a year. Okay, so then what do you think is going to happen at the next equinox, at the spring equinox? You're going to have the one sunrise at the North Pole for the whole year. So just think about that. You just get one a year of each if you are at the North Pole. If you're a little away from the North Pole, but above a certain latitude, then there's going to be at least one day where the sun never sets. At the North Pole, you're going to have 6 months of dark and 6 months of light. And people that live in situations like that, where the sun just, you know, they have night, day after day after day, it's just dark. A lot of times people have to have light that they expose themselves to simulate the daytime, because it can cause a depression called the seasonal affective disorder. Anyway, let's go on, unless you have any other questions about this. This is a pretty good figure to look at what things are happening. This is the path of the sun in our sky It's not at Memphis, it's someplace in the Southwest. I'm not sure what the latitude is, but it's a northern latitude. And it's lowest in the sky on winter solstice day, highest in the sky on summer solstice day. And in between, it's somewhere in between. Okay, so we got the axis tilt is the reason we have the seasons. Now, the variation in the seasons is not substantially, it's not from distance, but there are situations where the distance varies so much between one time and another in the year for some planets that it does matter, but it really doesn't for Earth. Okay, this is your local sky, and there's your zenith, and this is showing the path of the sun. It's on summer solstice day, the highest it ever gets if you're above 23.5 degrees north. So it rises in the east, it gets to its highest point, it crosses your meridian around noon. You can see it's clearly not at your zenith, but it is at a highest point, and then it sets in the west. At the equinox, it's lower, and at the southern, at the lowest point in the sky, it's our winter solstice. The sun does that, but it's at the lowest point. So in all cases, it's rising in the east and setting in the west, but how high it is in the sky is what's changing. Now, this is a picture taken at the Arctic Circle, a 24-hour time lapse. And it shows that the sun never sets at the Arctic Circle on summer solstice day. That's the lowest latitude before you start having, you've got to have a sunset sometime during the day. At this latitude or higher, there's going to be at least one day a year that does not allow the sun to set. It does get close, and when it gets close to the horizon, it's going through thicker amounts of atmosphere, and that's why it looks like a sunset color, orange and red and yellow. When white light goes through more of our atmosphere, the blue scatters away, and it leaves behind the oranges and reds and yellows. So that's why at both sunrise and sunset, we see that orangey color. Okay, oops, there we go. Now this is a completely different motion than we've been talking about. This is the precession of Earth's axis. And that takes a long time. It takes 26,000 years for Earth's axis to precess. And I have a top. Let me go get the top. I'm going to spin. So when you have a top and you spin it, gravity's trying to pull it over. And I think I can make it so that you can see this. Nope. Let me try again. My computer's in the way. Okay. Can y'all see that? You can see the top precess. I keep getting it too close to the computer. There you go. That's pretty good. Okay, so gravity is trying to pull it over, and it finally does. When it's spinning, it's going to lose some of that angular momentum because of friction, because of the contact there. Well, the Earth is like a top in a gravitational field of the sun. And because it's in that situation, it precesses, our axis precesses like that. So it doesn't change the degrees of tilt. It just changes which direction that axis is pointing. So like here, it's this far in this direction, but 13,000 years later, it's the opposite. The angles are the same. And it doesn't go, I don't know if I can show you this on here, but it doesn't just turn like that. Let me see if I can get this to where you can see it. I'm going to keep it at that same angle. You can just see my finger. It's ridiculous. Okay. It's like that. So I'm not going straight up ever. The axis is never straight up. It's just turning the whole thing around. Okay, well, 26,000 years ago, our North Star was Polaris, just like it is now. But 13,000 years ago, it was Vega. And sometimes we didn't have a North Star. Sometimes we won't have a North Star. It's a cycle that repeats and repeats. And a 26,000 year period is hard to detect, but the Mayans did. And I am so impressed with the Mayans and their astronomical data gathering and their insight, because they knew about this. They knew about this motion. We didn't even talk about this when we were saying, so how are all the ways that we move? This is another way that Earth moves. It precesses. Okay, that's a summary slide, another summary slide. And now we're going to talk about the moon. Finally, we're in section 3. And again, I wish I had my model, but we're going to do the best we can. Okay. So, that's not the slide I thought we would have. That's the slide that I like the best. Okay, let's just go with this one. All right, so if you pretend that Earth is where her head is, I think it makes the most sense. The moon is orbiting Earth. Okay, and it orbits Earth in about 29.5 days. In 29.5 days, it's right back where it was relative to the Earth. But moon phases depend on the sun as well. And so if you measure from one full moon to the next full moon, it's different. It's a different amount because you have to have a certain alignment of the Earth and the sun and the moon to have the different phases. So when the moon is between us and the sun, we don't see it because it's so near the direction of looking into the sun. The sun's too bright. We don't see it. That's also, if the alignment were just exactly right, that's when we would have a solar eclipse, a total solar eclipse or partial solar eclipse. But we don't have that every single month. We don't. And it's because the moon's plane of orbit is tilted 5 degrees from our plane of orbit. So when we have a new moon, most of the time it's too high or too low for an eclipse to happen. But whenever the moon is between us and the sun, even if it's too high or too low for an eclipse, that's when we say it's new moon. So now let's pretend this is the Earth, remember, and it's turning. So 12 hours away from looking at the sun, we're going to be on the back side of it looking into the night sky. Does that make sense? Are we going to see the moon there? No. Okay. We're not going to see the moon because where is it? It's in the direction of the sun. We're not going to see it back over here. It's over here. We're not going to see it in our night sky. When it's getting close to new moon, we can see it in the day. And we would see a crescent during the day, just several days before we have new moon. And then we'll see a crescent with the other side lit a little bit after new moon. So new moon is when the moon is in the direction of the sun, and we are not going to see it at night. So if you want to see something at night where you want as little light pollution as possible from anything else, let's say you want to look at a very particular galaxy, or you want like Andromeda, or maybe you want to look at the Milky Way, you're going to want to do that when it's new moon, because the moon adds light and it makes it harder to see dim things. So remember that the moon is going to go all the way around in roughly a month. So in one night, it's not moving very much at all, just a little bit. Okay, a few days after new moon, we have waxing crescent. Now, waxing and waning, you need to know which is which. Waxing is getting bigger and bigger and bigger. So we're seeing more and more of the moon lit. The moon isn't getting bigger, but the lit part of it is getting bigger. So a few days after new moon, we see waxing crescent. A few days after that, roughly a week after new moon, we see half of the moon lit, and it's the right half. When we look up, it's the right half. And we call it first quarter. We don't call it half moon. We call it first quarter because it's a quarter of the way around in the orbit. So wait a few more days and we see more than half of the moon lit. It's more of an egg shape, kind of an oval part that's lit. And it's still waxing. It's still every night we're seeing a little bit more of the moon, a little bit more of the moon. And then half a month after new moon, we finally get to full moon. We finally get to full moon. And it's in this position where the Earth is between the sun and the moon. If the alignment were just right, this is when we could possibly see a lunar eclipse. But for the same reasons that we don't have a solar eclipse every month, we also don't have a lunar eclipse every month. It's because the orbital planes are tilted from each other about 5 degrees. So if this is the ecliptic, this would be the lunar orbital plane. And they have to be where they cross for us to see an eclipse. So here we've got full moon, and then a few days later, and I forgot to tell you that this oval shape is called gibbous. So this is waxing gibbous. When it's the right-hand side, it's getting bigger, waxing. And when it's the left-hand side that's lit, it's waning. It's getting smaller every night. We see less and less of the moon lit. So we go from full moon to waning gibbous. A few days later, we're at third quarter because we are 3/4 of the way around in the orbit. Then a few days after that, we get to waning crescent. And a few days after that, we're back to full moon. Notice that if you're not looking at the moon from Earth, let's pretend that you're looking at the moon from some other place that's further away. Just like we're seeing in this, our view of the moon in this slide. Notice that the side towards the sun is always lit. The side away from the sun is always dark, as it should be. It's just because we are inside the orbit of the moon that we see these different phases. Do y'all have any questions? I'm not done. I'm not done with this slide. But before I go on, does anybody have any questions? Okay, let's think about the time of day that these phases happen. Okay, new moon would be highest in your sky around noon. The sun is highest in your sky around noon, and it's in the direction of the sun. Okay. Waxing crescent is highest in the sky. Remember, it's a few days later. It's mid-morning. And I was going to say that's not right. And I see that I read the top line instead of the middle line. I thought, that's not right. That's not right. It's got rise, highest, and set. Rise, highest, and set. So just pay attention to the highest. When is this phase highest in your sky? Mid-afternoon. So this happens at noon. A few days later, we have waxing crescent mid-afternoon. A few days later, we have first quarter at sunset, highest in the sky at sunset. A few days later, it's highest in the sky late in the evening, and full moon is going to be highest in the sky around midnight. Now, that progression means that when the moon is waxing, it's going to be afternoon and evening hours for you. It's not morning. If we continue from full moon, a few days later, waning gibbous is highest in the sky before dawn. Third quarter is highest in the sky at sunrise. And waning crescent is highest in the sky mid-morning. And then we're back here to new moon around noon, a few days later. So think of this part highest in the sky in the afternoon and evening, and this part highest in the sky after midnight and in the morning, leading up to this position. But just remember that this takes a month, and the whole time the Earth is turning once a day. So everybody sees the same phase of the moon. Everybody on Earth, if they can see the moon, they're seeing the same phase in any one day. So if you're seeing first quarter in your sky, then everybody else that can see the moon is seeing first quarter that day. All right. You may want to come back and refer to this. Oops, I keep doing the wrong move. There you go. So this is a summary of the 29.5-day cycle of phases. It's from new, crescent, first quarter, gibbous, but they're leaving out waxing. They're just putting a big bracket and saying, okay, all these are waxing. And then full moon, and then the waning phases. So it's 9 a.m. You look up in the sky and see a moon with half of its face bright and half of it dark. What phase is it? Put it in the chat. One brave person. Okay, 2. Just think about what phase you would be seeing at 9 in the morning if you see half of the moon lit and half of the moon dark. Okay. I've got all different answers. All different answers. Let's look at this. Let me go back. Okay. Here's where half the moon is lit. Here's where half the moon is lit. got to be one of these two. How do we tell which it is? It's either first quarter or third quarter. Which one is up in the morning? Remember, these happen highest in the sky in the evening, in the afternoon and evening. These happen after midnight and in the morning. So it's going to have to be third quarter, which is C. Half moon, we may talk about seeing half of the face of the moon lit and half dark, but half moon is not a phase. It's first quarter or third quarter, because it's either a fourth of the way, first a quarter of the way around or 3/4 of the way around. Okay. So that's just an example that you can, the other thing is, look at this. You can see that waxing phases have the right side lit and waning phases have the left side lit. So if you saw this, if you knew that, you'd know it was third quarter, but we didn't see a picture. We were just told it was at 9 a.m. Okay. All right. This is kind of tricky. You may have always heard that we see one side of the moon, and I don't know if you have or not, but it is true. We only see one side of the moon from Earth. It does rotate on its axis. It does go through what you would call a lunar day when it completes one rotation on its axis. But the weird thing about the moon's day is that it is the same amount of time. It's the same amount of time as its revolution. I know it's 12:25. I'm going to stop here, but I want you to think about if the moon did not rotate as it orbits the Earth, we would see the other side of the moon. But we don't, because it does rotate. Its rotation period is the same as its revolution period. And so if this, notice this person's face is always facing this central ball. So that's like us, that's like the Earth, and her face is like the moon. So she does a rotation. She also does a revolution. We never see anything but a face. Okay, thanks for coming. I hope we'll be back in person on Friday, and hopefully we will finish up this chapter. We're going to talk about eclipses, and then we'll go on to the ancient mystery of the planets.
Bye.
Bye.